All right, so here is the review video that I had promised. Yeah, so technically we're doing 4 chapters, but I'm just going to break it up into 2 chapters where chapters 10 through 12 are going to be all the rotation stuff. And then chapter 13, of course, is all the gravitational stuff. So let's talk about each one of these. So first, let's start off with chapters 12 or 10 through 12. So first things that we looked at were center of mass. About center of mass. So center of mass is the position of the center of mass is then equal to the sum for I of MIRI vector notation, divided then by the sum over IMI, where the sum over IMI is equal to the total mass. So again, this is just a weighted average, but again, this is only for discrete objects. If we have non-discrete objects, if we have continuous objects, then in this case, this is going to become equal to the integral. So this is then going to be to the position r integrated over the differential mass divided by the integral over the differential mass. This is for, again, continuous objects, where the differential mass, as we've seen before, can be written as one of 3 ways. So either lambda dl for line symmetry, sigma dA for area symmetry, and finally rho dV for volume symmetry. So obviously this thing is position dependent. So if I choose different coordinate systems, I'm then going to get different results, at least for the position of the center of mass. So that's that one. Next up, we saw then rotational kinetics or kinematics. So in this case, we have angular displacement or angular position, depending on how we want to look at it. So in this case, we had that the angular displacement delta theta then was equal to the final angular position minus the initial angular position, right? And then we have angular acceleration. So omega average is equal to our angular displacement divided by our change in time. Again, this is only for the average. And then the instantaneous then is equal to the time rate of change of the angular position. And then finally, angular acceleration is how quickly the angular velocity is changing. So in this case, the average angular acceleration will then be the change in angular velocity divided by the change in time. So it's going to be equal then to the final angular velocity minus the initial angular velocity divided by my change in time. Or again, instantaneous, we just take the limit as delta t goes to 0, which means this guy's going to become an integral. So this is the time rate of change of the angular velocity, which is then equal to the second time rate of change of the angular position. So again, these are all exactly the same definitions as the just position, regular velocity, or linear velocity, and linear acceleration. These guys then also follow the same kinematic equation. So we have the same 3 kinematic equations. So we have first, omega is equal to omega initial plus alpha times the time. Second one then is we have theta then is equal to theta initial plus the initial angular velocity plus 1/2 the angular acceleration times the time squared. And then finally, the third one is my angular velocity squared is equal to my initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. Now, the angular quantities are related to the linear quantities in the following sense. So if here is a circle at which it's moving around, so in this case, right? So if my point starts here and then ends up over here at a later time, then in this case, this thing sweeps out this arc here. So in this case, it also has an angle at which it sweeps out. So here the arc is equal to theta times the radius, where this thing has some radius of r. So this is the relationship between the translational distance and the angular distance here. Next off, this thing then has a tangential velocity and possibly a tangential acceleration. So this is my tangential velocity. So the tangential velocity is equal to the angular velocity times the radius. So if this thing is rotating about in this direction with a velocity of omega, that's how these guys relate to each other. And then finally, if this guy is speeding up or slowing down, let's say it's speeding up. So in this direction, I have a tangential acceleration, where my tangential acceleration is again related to the angular acceleration. So how quickly the angular velocity is changing times the radius of, again, a circle. So these are tangential to the circle, but these are the relationships between all of these guys. And then finally, this thing also has a centripetal acceleration, which is pulling it towards the center. So this is my centripetal. So my centripetal acceleration is either the tangential velocity squared divided by the radius, which is also equal to 4 pi squared times the radius divided by the period squared, which is also using the first equation here for tangential velocity. This is then also equal to the angular velocity squared times the radius. So any one of these guys is sufficient, just depending on the information that which it is that I know. So good. So that is a redo of angular kinematics. So next up, we have then rotational kinetic energy. So for rotational kinetic energy, this then turns out to be 1/2 I times omega squared, where I is what's known as the moment of inertia, which is then equal then to the sum over I of mi times ri squared. And this is only true for discrete objects, or at least objects where we could sum all of them together because we already know the moments of inertia. So for example, I have one thing stacked on top of something else. And then for continuous objects, this guy would then be equal to the integral of r squared times dm. So for continuous, where again, dm is the same as on the previous slide. Fantastic. So again, moment of inertia is simply the angular analog of mass. So in this case, all that means then is what? Since mass is a resistance to linear acceleration, that means angular or moment of inertia is the resistance of an angular acceleration in that case. To use this, instead of actually doing the integral, as long as we know the moments of inertia of the center of mass, we can then use the parallel axis theorem to move the pivot point to any other location using the parallel axis theorem. So parallel axis theorem simply says that, watch, if this was my object, and let's say this is my center of mass location, but I want to move my pivot point to some other location, let's say that's, I don't know, over here. So this is the new pivot point that I want. And then this is the distance d, which is the distance from the center of mass to the location of the pivot points. The parallel axis theorem simply says that the moment of inertia about that point p is then equal to the moment of inertia about the center of mass plus the mass of the object, so the mass of m, times that distance v squared. So on the exam, I'm pretty much not going to expect you to do the integral because I know a lot of you are still in Calc 1, so you haven't actually learned how to do the integrals yet. But so what you'll have to do is actually use the parallel axis theorem to move the pivot points. And in this case, I'll give you on the front page a list of moments of inertia, and then you just choose the one that actually fits the object itself. So that's rotational kinetic energy. The only other thing then is when I have a rolling without slipping. So for example, if my object is here, rolling across the ground. So as we know, there's static friction acting on this guy to cause it to rotate. Static friction would be in this direction, causes him to rotate this way, but he's also moving forward with a center of mass velocity. So the center of mass, and this is my omega. As we talked about in class, what happens in this case then is the total kinetic energy becomes equal to 1/2 the mass plus the moment of inertia about the center of mass divided by the radius of the object squared, all times the center of mass velocity squared. So this is the radius of r. So this is always true with rolling without slipping, just automatically default that this is my total kinetic energy, which as we talked about in class is both the translational, which is the first term with the mass here, and then the rotational, which is the second term here. So it's simply those two added together. And then we're relating again under this expression here, the rotational velocity to that of the linear velocity. So that's pretty much it. So basically in conservation of energy, if you have something which is rotating, then you have to just add on the rotational kinetic energy. Remember, there is no rotational counterparts of gravitation because all we care about is the center of mass. So just look at where the position of the center of mass is. So good. So next up, we then have torque. Talking about torque. So torque is the analog of force. So this is the rotational analog of force. So this guy is defined as R cross F, or the magnitude of the torque then is equal to the magnitude of the moment arm times the force that which it's applying to get the torque times then sine of the angle between the two. So what does this mean? So this means that if this was my object, something like that, and this is my pivot point, okay, and then my force is, I don't know, say acting here. This is my force, whatever that force happens to be. In this case, again, R is the vector which points from the pivot point to the position of the force. And then if I extend this just a little bit further, then theta is the angle between those two guys. Now, if the force causes a clockwise rotation, which is what this one is going to do, that's going to cause it to ultimately move this way. This is what we consider a negative torque. But if it causes it to have a counterclockwise rotation, that then is a positive. So from there, we modify then Newton's second law. So Newton's second law then says that the sum of the torques is then equal to the moment of inertia, because that's the angular analog of mass, times the angular analog of the acceleration, which is the angular acceleration. So that's it. So this works exactly the same way as forces do. So you just write out the sum of the, well, you draw a free body diagram, you label all the forces, and then anything that rotates, you have to put on torques, which are just regular forces that are acting at some position, not at the center of mass. And then, yeah, just determine it that way. From there, then we did statics. So statics is when the sum of the forces and the sum of the torques must both simultaneously be equal to 0. So this is statics. Let's see, what else did we do? We did rotational work. So rotational work, if I have a constant torque, so torque is equal to a constant. In this case, the rotational work is then equal to simply the torque times the angle at which this thing is rotated. That the torque is rotating the object anyways. If it is non-constant, if my torque is not equal to a constant, in this case, we have to integrate. So in this case, the rotational work is then equal to the integral of the torque integrated over the angle from the initial angle to the final angle. And finally, we have that the rotational work is related to the rotational kinetic energy by, again, the work kinetic energy theorem, which says that the net rotational torque is then equal to the change in rotational kinetic energy. And then last thing we finally did then was angular momentum. Angular momentum. Awesome. So for angular momentum, we simply have that for a point particle. For point particle, in this case, drawing a quick coordinate system here. So x, y, and z. Let's say my particle sitting here, mass of m. Say he's moving in this direction with a velocity v, so his linear momentum will be in the same direction. So it's my linear momentum. Then we have an r vector, which points from the origin to the location of him. I'm going to extend him just a little bit in this direction. Will be evident in a second. So in this case, we say he has an angular momentum, which is then given by r crossed by p, similar to the torque, which is r crossed by f, or magnitude-wise, this is going to be r times p times sine of the angle, where again, the angle in this case is the angle specifically between the r vector and the momentum. So great. Other thing, how about this thing, is that the time rate of change of the angular momentum is simply equal to the torque, just like way back in exam number 2, the time rate of change of the, or sorry, exam number 3, sorry, time rate of change of the momentum is equal to the force. This guy has exactly the same relationship. So again, this is only true for point particles. Now, if I have a continuous object, let's say, again, this is my continuous object where this guy's rotating with an angular velocity of, let's say, omega about this particular pivot point. My pivot point's P. This guy says that the total angular momentum then of this object is equal to the moment of inertia about that pivot point times the angular velocity. So this is the moment of inertia of a extended body, continuous object, or what we call more specifically a rigid body. So a rigid body, again, is one that does not deform under rotations. So something like a ruler, a pen, a wheel, anything like that, anything that doesn't change its shape as we rotate it. So this also says then that what the time rate of change of the total angular momentum then is again equal to the torque. So this is going to be equal to the external torques acting on the system. Now, if the external torques acting on the system are equal to zero, in this case, we have conservation of angular momentum, which says that the time rate of change of the angular momentum is equal to zero, which means the change in angular momentum is equal to zero. Hence, the initial angular momentum must then be equal to the final angular momentum. From here, what we care about is the same thing we cared about with regular momentum, which is collisions. So again, in general, we have the three collisions. So again, we have elastic, inelastic. Oops, that was spell. There we go. Inelastic. And then finally, completely or perfectly inelastic. Awesome. What happens in elastic versus inelastic is just that energy is conserved. So here we have to have that's what our change in rotational, well, I should just say total kinetic energy. So the change in kinetic energy then is equal to zero, which means the net initial kinetic energy must be equal to the net final kinetic energy, which means that includes both translational and rotational kinetic energy. So if one thing is moving in a straight line relative to some pivot point, in that case, then it has to have an angular momentum. So that's translational, but then afterward, let's say something is rotating. So in that case, there'd be possibly both translational and rotational. So for this one, the kinetic energy, of course, is not equal to zero, which means only angular momentum is conserved. And then finally, for completely inelastic, again, these guys stick together. So that's it. So these are all the equations for chapters 10 through 12. So next up we have, or one other thing I'll point out here before we move on, is the best way to remember all these things, again, is using our replacement scheme. We've been writing down every time. So this is our replacement scheme. Good. So the replacement scheme is simply going from linear to angular or rotational, write it that way. So the replacement scheme is simply that x goes into theta, v becomes omega, a becomes alpha, but m becomes the moment of inertia, the force becomes the torque, and then finally the momentum becomes the angular momentum, either capital or lowercase angular momentum, depending on what it is I'm talking about. So I should write it this way. So technically, capital P is the total, and that's going to be the total here. Be a little more concrete about that. So anyways, so again, if you remember the linear, all you have to do to get the rotational is simply turn it into the appropriate variable. So again, when it comes to the three kinematic equations, for example, the first one, so you get what? V is equal to V naught plus A times T. So that just becomes equivalently omega is equal to omega naught plus alpha times T. So again, they're exactly the same structure. Everything works the same way. All we have to do then is make that replacement. Or again, Newton's second law says the sum of the forces is equal to mass times the acceleration. So the angular version is that the sum of the torques is equal to the moment of inertia times the angular acceleration. So again, as long as you know the linear, you can easily come up with the rotational by making those replacement schemes. So good. So next up, we got chapter 13. So this is our gravitational chapter. So here, what this one says, and again, so I have two objects, M1 and M2, which are spatially separated from center to center by some distance of R. So this is my distance R. These two are both going to feel an attractive force. So this is then F1, 2. So the force on 1 by 2. This one's going to be pulled in this direction along the line that connects the two of those. So this is the force on 2 by 1. So Newton's universal law of gravity says that the force on 1 by 2 is then equal to negative gm1 m2 all over the distance r squared in the r2 hat direction, where the r2 hat direction is the unit vector which points from the second to the first. So F12 is in the opposite direction of that. And as we talked about, this satisfies Newton's third law, which says that the magnitude of the force on 2 by 1 is equal to the magnitude of force on 1 by 2. They just point in the opposite direction. So this is, again, satisfying Newton's third law. So good. Next up, we then have superposition principle. So superposition principle just simply says if I have a whole bunch of different masses here, I'll just draw 4 of them for now. So I got 1, 2, 3, and 4. Then we can determine then the force on, say, the fourth one by looking at all the forces from all the other ones. So in this case, it's going to be pulled in this direction by the first. So it's going to be the force on 4 by 1. He's going to be pulled in this direction by him. So it's going to be the force on 4 by 2. And then finally, it's going to be pulled in this direction by him. So it's going to be the force on, 4 by 3. So his total force on him, I don't know, might point off in this direction, depends on the size of all these guys. So let's call that force on 4. So superposition simply says that the total force on the fourth object here is then equal to the sum over I, not equal to 4, of then the force on the fourth by the ith particle. So basically all this means is you're going to determine all of the pairs of forces on 4. So again, force on 4 by 1, force on 4 by 2, force on 4 by 3, and then simply vector sum them all together. And then finally, if I have some sort of continuous object, so this is a continuous object with the total mass of, say, capital M, and then I'm looking at the force of this guy at little m, and then again, we're going to chop this thing up into a small piece of dm. So here's my dm, where dm then is going to be some distance of r away from that guy. So this guy then says that the force on m is then going to be equal to minus g times m times the integral of dm, all divided by r squared in the r hat direction. So, and again, dm is exactly the same dm as it was before. So this is what happens when I have a continuous object. Next up, what did we talk about? So we did all that. Oh yeah, gravitational potential. So now we get gravitational potential energy is equal to minus G M1 M2 divided by R. So again, this just looks at the picture of M1 and M2, again, separated by some spatial distance, center to center of then R. So in this case, this is talking about the gravitational potential energy between the two of those. And again, it's negative because this thing is attractive, which simply means that here's R, here is the gravitational potential. So the plot of this guy looks something like that. Okay, so that's what this guy looks like. Let's see. So that means we can start using conservation of energy. So conservation of energy then just simply says that the change in kinetic energy plus the change in now this type of gravitational potential energy is equal to 0. And in this case, it's always going to be equal to 0 because we're going to ignore any type of resistance, mostly just because we're out in space is basically what we're going to be playing with. So think about this as 2 planets way out in space. So there's effectively nothing in between the two, just mostly just vacuum. So there's no particles or anything to cause air resistance. So that's that guy. So good. So this guy we're just going to use simply for conservation of energy. So from this, we can then determine what's known as the escape velocity. So the escape velocity is if I took some object, let's say like a rocket here, and I put it on the surface of some planet here. So initially it starts off at the radius. This thing has a mass of capital M. What this thing says then is this is the amount of initial velocity I need for this thing to completely escape, go all the way out to spatial infinity, where it's going to stop. So the final kinetic energy is going to be 0. So the escape velocity, as we found, is equal to the square root of 2 times g times the mass of the body here. So the one that's being escaped from, divided by the radius of the body. Awesome. So that's that guy. Great. And then next up, what we saw was orbits. Talk about orbits. So things like moons and satellites and etc. So this one simply says that, again, if I have some body which is being orbited, so here's M, capital M, and then here's the orbiting body. Happens in this case then, again, is it's going to feel gravity pulling in this direction. So here's the gravitational force. And in this case, we then can find the tangential, or the orbital velocity this thing needs to stay in orbit. So this is the orbital velocity, which is also equal to the tangential velocity. So my orbital velocity, as we found, is equal to the square root of g times the mass of the central body divided by the radius of the central body. So we don't care about the mass of the object, which is orbiting, only the orbited body. This, of course, has a period associated with it. So we know that's what, sorry about it this way. So, oops, sorry. That's not that R. It should be this R. Sorry, that R that up is actually this distance, which is the distance from the center of the orbited body to the location of that object. Great. Good. So from this guy, then we also have the total energy of what he is in. So my total energy at this particular altitude here, at this height, is then equal to minus the kinetic energy. So this guy is equal to minus g times the mass of the central body times the mass of the orbiting body, all divided then by 2 times the radius at which it's at. So this is my total energy. Let's see, anything else here that was useful? There's a period associated with all that, but pretty much about the period. So I just remember the period. So 2 pi times the radius at which it orbits then is equal to the orbital velocity times the orbital period. So you get the orbital period that way. What else? So lastly, go with Kepler's law. So this is actually where we really get the orbit from. Let's talk about Kepler's third law. So Kepler's third law actually says that the orbital period is equal to 4 times pi squared divided by g times the mass of the body which is being orbited times the radius cubed at which this guy is actually rotating about. So this is Kepler's third law. We can actually get that directly from the stuff we wrote down about the orbits. But anyways, this is Kepler's third law. So Kepler's third law, again, relates the period, which is our orbital period. That's how long it takes for this guy to move around through a full complete circle, to the radius at which this guy is orbiting. So I think that's pretty much it when it comes to chapter 13. Yeah. So yeah, so that's it. So these are all the equations that you would need for Monday's exam. And sorry, I forgot to put this up earlier. So honestly, I got so busy with my kids yesterday that I completely forgot. Thank you, Sam, for reminding me to post this guy. So yeah, I'll post that, and yeah, I'll have the solutions to the practice problems up here in just a minute. All right. So good luck, and any questions anybody has, just feel free to email, and I'll get back to you as soon as I can over the weekend. Other than that, I'll see everybody on